Alright, so let's now derive the equation of current flowing inside the channel of a MOSFET, of an NMOS to be very specific. So, as we know, this is the structure of a MOSFET, and let's go ahead and derive the equation for it. Now, when you say a MOSFET, you're talking in terms of micro, nano devices, nano-sized devices, but all you have to understand it's just a device carrying current. It's just a device through which a few electrons are going to flow, only smaller. So it's going to obey the same definition of a current, right? So what is the equation of a current defined as? So, hold on a second, let me just get a good color here. There. So current given by I is the charge flowing across a cross-section of an area in unit time. If you see, say this is the cross-sectional area that the current has to pass through, and this is an electron, and it hits this place. If you're here, suppose this is your eye. It nowhere looks like an eye, but let's just consider it's an eye for now. This one electron hitting this place in 1 second constitutes Q. Q, which is the charge of the electron, per 1 second. So that's your current. Alright? Say 2 electrons hit the place in 1 second. You have 2Q. Say 3. So we have 3Q. So suppose we have a group of electrons in one place, and we call the density in that place, the current density, and we call it QD. So you're going to have I equals to QD amperes or current in that 1 second if they hit this place in 1 second, right? But suppose they have a velocity, alright? So consider this small space here, and we have QD amount of electrons here, and the length of this section is 1 meter, and their velocity is 1 meters per second. So in 1 second they travel this place and they hit this area of cross section where you have your eye. So your current is again QD, but suppose their velocity is bumped up to 2 meters per second. You're going to have twice the number of electrons. Just suppose it's, as and when you deplete this place of electrons, you get more electrons here. So you're going to get twice the number of electrons here, right? So your I is then going to be 2 QD. If you beef it up to 5 meters per second, you're going to have 5 QD. That means the equation of current can be boldly written as QD times the velocity in meters per second. Remember this V here, let me highlight it. Hold on a second. This V here is not the voltage, it is the velocity. Okay? Don't forget that. So this is the equation, the general equation for current flowing in a MOSFET. We have to here before we can call this as the ruling equation. Let's go ahead and derive the more accurate equation for this. Alright? Okay. So, before we do that, let's look at what all terms our equation for the current have. If it's current, it definitely has to have some sort of voltage terms in it. That's one. And if you look at a MOSFET, it's a three-dimensional device, right? It's a real device. So this is the gate, This is the source, and this is the drain. So the length of the channel and the width of the channel do matter, because it's going to hold so many more electrons, right? Instead of just a sheet or just a sliver of the material. Alright? So you're going to have the width of the channel, the length of the channel included. What else would you have included in it? Because you're applying gate voltage or drain voltage or source voltage, but the gate voltage is going to get to your channel once it is through the oxide layer, as shown here, right? Now, if that oxide layer is present, it does have a capacitance, correct? Whoops, I don't know where all this gone. Okay, let's do it again. So it's V, W, L, and C ox. Okay, C ox is the capacitance of the oxide. So even that's going to play a big role. Well, we have all these terms, but do you think there will be some more? There will be just one more term. Let's consider a small, funny example actually. Let's consider a classroom. This is a row, and this is a row of students. They're all sitting here. I'm not drawing their bodies, just their heads. And this is the space in between two rows that a teacher can walk into. Say these students here want to trouble the teacher, and they stick their legs out here, and they keep their bags outside and make it difficult for the teacher to walk through the place. If the teacher had a velocity of v, it's still going to be retarded because, the velocity is going to be reduced. It's because of all these students disturbing the teacher. If they don't have their legs stuck out of the row, he can pass through easily. He can pass through with his own velocity, correct? So what is the thing that makes the teacher move faster or slower? It's the crowding. It's the crowding of something in this row, correct? So in a channel, you're going to have other stuff, not just electrons. Okay? So based on their crowding, the electrons are going to be able to be more mobile or less mobile. To present a magnitude of their mobility, we bring in a new term that is called mu n. N because it's an NMOS. Okay? Where electrons are the carriers, are the charge carriers. So in a nutshell, your equation for current is going to have these 5 terms for sure. Alright? Well, let's go and derive it properly. We said the current is given by QD times the velocity, correct? Alright, let me change the color of the pen here. It's getting boring. Let's use a bright yellow. Okay. So let's first look at what QD is all about. From the capacitance of a capacitor, we know that C equals Q over voltage. Capacitance equals charge over voltage. That means charge equals voltage times capacitance. Okay? Here, the only capacitance we're going to deal with is the capacitance of the oxide, correct? So let's write that down. Now, for the voltage. Let's look at the effective voltage inside the channel of a MOSFET. Let's just draw the channel here and the oxide here. Okay? Oxide. And I'm giving a voltage, VG. And the source and the drain are both grounded. Okay? So whatever VG I give, let's call it VGS for now. It's not going to matter because the source is anyway grounded. Let's look at how much voltage will be available in this channel. It's very simple. Consider a human being, and he has to jump over this wall to get to the other side, and he has 400 biscuits amount of energy stored in him. And suppose he comes here and he's left with 300 biscuits. Well, what did he lose here? He had to spend 100 biscuits to get over the wall, correct? To get over the obstacle, correct? So what we have to look at here is the remaining, or the effective energy he has once he gets past the wall, is total energy minus the energy needed to go over the wall. This energy needed to go over the wall, in our case of oxide, is called the threshold voltage. Okay, it's not 100. I just gave that to you as an example. Okay, so VTH here would be subtracted to get the effective voltage inside the channel. So, coming back to your definition of the charge, is equal to capacitance of the oxide times the effective voltage, which is VGS minus VT. You can call it VT or VTH, and it really doesn't matter. Okay. Now again, the capacitance of the oxide is just for, as I said, just for one sliver of the channel. Alright? For the entire channel which has a width of W, your capacitance is going to be times the width. Okay? So let's say QD is W times C ox VGS minus VT. We already have a lot of terms. If you look at the terms that you wanted to get for our current equation, we already have a few. It's amazing. Okay? So we'll come to that. We'll come back to this. Now, consider a case where you have a channel. Let's draw the oxide. We have the VG, and now I'm giving a positive voltage VD to the channel, and the source still remains grounded. Okay. Now, by providing VG, what happened? From our previous lecture, you can remember that from zero channel, we developed a channel of some thickness, right? How did it happen? When VG is positive, it repelled all the positive charges here, or the holes here. It made them go away and develop a empty space for electrons to come into. Correct? That means, so the more positive we got, the thicker the channel got, right? Now what we're doing is we are providing the same VG, but we're providing another VD here. Okay? But it is lesser than VG. It is a positive voltage, but lesser than VG. What happens when this is lesser than VG? The thickness here is going to reduce. Why? Because it's going to repel the holes here lesser than VG repels the holes here, correct? That means what happens? The holes travel upwards because they're not repelled as much as VG. Okay? So what happens is the path for electrons looks like this. As you increase VD, the path goes on decreasing towards that side. Okay? That means, and when you come to this part, when it really touches that layer, it's called a pinch off. But we don't have to really worry about pinch off for now, for this lecture. We can come back to that later. So what I'm trying to say here